we've heard today a lot about the application of GIS, but I'm here today to talk about the importance of data quality in GIS. So whenever you're looking at spatial patterns, the input data you put in is vitally important. One very common application that we see in GIS is species distribution modeling. For example, if you look at the scholarship posters that are out downstairs and just over by our office, many of them have applied species distribution models. Species distribution models, also known as SDMs for short, ecological niche models, habitat suitability models, and many other names, are very simple in concept. They take presence and absence records, also known as occurrence records. When absence records are not known, pseudo-absences are used in their place. A pseudo-absence is a location where a species has been sampled or not, but is not known to be present. These are then related to spatially explicit environmental predictors, which are run through an artificial or machine learning algorithm to provide an output of the predicted probability of occurrence or some other output depending on the objective of the study. However, these models assume that the occurrence records are geographically accurate and the corresponding environmental predictors describe this niche of the species being examined. This is where data quality comes in. If either of those assumptions is invalidated, the resulting model output is potentially unreliable and inaccurate. And this is a very common case in many different species. So the species that I examined in this case were mosquitoes. So everyone knows the nuisance that is a mosquito, especially in the summertime, but they're also very epidemiologically important as they cause approximately 1 million deaths per year through their ability to carry and transmit diseases. And as global climate increasingly warm, we're seeing new pathogens introduced into new regions by invasive mosquitoes as they can now spread further and further north. However, when it comes to their data, some of the most important mosquito species, which are the Aedes albopictus and Aedes aegypti, commonly known as the Asian tiger and the yellow-fever mosquito respectively, are privacy protected. So for example, in North America and parts of Europe, these records are only available as a centroid of an administrative boundary. In this case, in the US, it is the US counties. In Canada, it's the health regions. In Mexico, it's the states. And in Europe, it's the corresponding counties as well. Now, these species can carry and transmit over 20 different pathogens to new regions and are among the most globally invasive species. Their ability to inhabit microniches when the overall climate is no longer suitable allows them to spread rapidly and introduce new pathogens at an alarming rate. So the issue comes with the centroids. So when you're limited to a centroid, the geographic accuracy is significantly off within the concept of administrative boundary. Previous research has shown to account for those centroids, you have to take the mean within the area of the geographic inaccuracy. So in this case, the US counties. But as you do that, you lose significant environmental detail, which can drastically alter the resulting predictions. In the case of mosquitoes, because they inhabit microniches, that could be as small as a cup of water or a single tree. So across a US county or other administrative boundary, which for the record has an average size of over 6,000 kilometers square, using this type of analysis raises significant concerns on how reliable the resulting predictions are. So for example, to illustrate this, in 2017, the Center for Disease Control and Prevention published a maximum entropy species distribution model examining the distribution of Aedes albopictus and Aedes aegypti. At the time, it shows that up in Michigan, they were unlikely to occur. However, when this paper was published, just across the border in Windsor, Ontario, Both species had already occurred the year previously and continue to occur until 2022 for Aedes albopictus, and while 2021 for Aedes aegypti. This area is now considered the first established population in Canada by the Windsor-Essex Health Unit. So with that in mind, we have to question if using these centroid occurrences within species distribution models is reliable. Further, within species distribution models, there are many different factors to consider in relation to the predictor variables and the occurrence records, as well as the algorithms selected. So there are easily over 40, if not 50, different algorithms within the literature that people easily choose between. With all of the decisions and the data, the issues with the data quality available, can we even really use these? So this is one of the different questions that I looked at during my master's research, which is what I'm presenting. So to analyze this, we first had to have a known distribution at a very fine geographic scale. So to do that, I created an artificial species, also known as a virtual species, that was designed to represent both Aedes albopictus and Aedes aegypti. So I used the main environmental drivers of annual temperature, which suggests how well a species of mosquito can survive and reproduce, while precipitation of the wettest month and elevation indicate the availability and quality of ovary deposit locations, in other words, where they were laid their eggs and could survive. These were based off of laboratory studies of their physiology to create the habitat suitability index, which was then output into a geographically explicit probability of occurrence to test against. This probability of occurrence was divided so that the US was considered the training region, while the North America, Canada and Alaska was used to test the accuracy of the model. So to do that, created a binary distribution of presence and absence within the US and Mexico, which was then converted to centroids for any US county or Mexican state with one or more occurrence record. As true absence records are rarely available for mosquitoes, we use pseudo-absences in its place. I varied these at different levels of ratio from equal, double, triple, or set 10,000, which is commonly used in species distribution models. And I also varied the predictors. So in species distribution models, often we don't know exactly what is driving species distribution. So you put in all variables that you expect and then return the ones that are most statistically significant. But we also tested the 3 that were originally designed to use the model or design species. And I tested 25 different algorithms over 100 repetitions and 1,500 iterations to create a very large and statistically sound sample size. To evaluate this, I conducted a full diagnostic metric of any artificial intelligence. Today, I'm only going to present a quarter of that for sake of time. So this was in relation to how well it's calibrated, how much the bias was included, the skill, the overall forecast accuracy, and the variation with the variation of predicted versus expected values. This was validated over 3 different conditions. So within the training area, which was the US and Mexico, and within the testing area, which is Canada and Alaska, and then a comparison between T2 to show fit. So in terms of artificial intelligence and machine learning, fit should be as small as possible. If it's the training area is greater than the testing area, that means it's overfit, and it's only able to successfully predict the data is given, not additional data. Then I conducted a type 2 chi-squared post hoc, type 2 post hoc chi-squared with 9-cent correction. And as I had over 30,000 models, I evaluated them on a relative scale using total relative performance per metric, determined across all the different validations and ranked them from poor good, average, and excellent. As a result, we can see that in most cases, the centroids only were able to pick up either the highest suitability areas, but significantly over-predicted where unsuitable habitat was. So we just compare what we were expected to see versus what we actually saw. Even in the best models, we can see that it lost all the low variation of somewhat suitable area. But it did significantly always picking up the high suitable areas in Mexico and the southeastern United States. As model performance degrades, we can see that that pattern becomes increasingly worse. And the poorest models, it drastically over-predicted where the species was going to occur. So this raises significant concerns with the application of these types of data, as you have to be very careful as to which algorithms you're using and the corresponding methods, because otherwise the predictions are not overly accurate. The most accurate positions for these models was in the directly adjacent from the training areas. So as the predictions increased in geographic distance from the training data, the US and Mexico, the quality of predictions decreased, which is also significant because for these type of applications, normally that's what they're looking for is much further in geographically or in time from the training data. But overall, if you are very careful with the algorithms and methods applied, it was able to provide a marginally useful example of data within not too far geographic distance. So in general, generalized boosting methods or weighted ensemble methods tend to be the best. Both of these algorithms use a variety of sampling methods and interpreters to create the resulting output. And it was required for equal presence and absence data. As you increase the absence data, in this case, it tended to overfit the data even more because it's considering even more of those counties as unsuitable, not much higher rate, which is proven to be invalid in this case. While the predictors, even though we did consider what theoretically should have been the best, which is only using the 3 predictors used to design species, with the change in scale from the original 1 kilometer to over 6,000 kilometers, it drastically affects how the predictors are interpreted. So using what was statistically most important allowed the model to interpret how the species are responding at the scale or resolution that the model is being interpreted at, not the truly what is ecologically happening, because we don't have that data to go into the model for it to interpret accordingly. So with that, species distribution models from centroids can provide marginally useful results in the application of epidemiological species, but it's very important to consider the accuracy of your data as well as what algorithm you're using. So for anyone looking to use species distribution models, it's always important that you test for the given data and the objective to ensure you're reaching an appropriate conclusion. It's also important to note that one of the most popular algorithms, maximum entropy, which is what the CDC used in the model I showed, only provides an average, if not poor, performance overall. So even though it's the most common, it may not always be the best in all situations. So one important thing to note is that all of this work was done in R in comparison to previous talk, which was done in ArcGIS. So here at Magic,